So, welcome everyone. My name's Terry Humphreys and I'm here from Curtin University, and I'm just going to give a little introduction into tonight's event. So I'd like to acknowledge the traditional custodians of the land we're meeting on today, the Wurundjeri people, and I wish to acknowledge their elders past, present and emerging. I'd like to start by thanking our sponsors of this event, Chem Centre. They sponsored the whole Chemaraderies series, and so yeah, we thank them very much. And tonight is actually co-badged with Proxa, so they've supplied the food, and so thank you very much, Neil. It's delightful. Without further ado, here's tonight's main event. So I'm going to pass over to Tamsin Collins, who's done a fantastic job of organising this, as well as the rest of the industry group. And so, yeah, over to Tamsin. Thank you very much.
This year, our seminar for the water, or for the industry group, is around water. So last year we did it on aluminium, and this year it's water. And that was largely based on who are the members within RACI. They were sort of the next biggest group that we had. So we want to cater to our members, but also the fact that water is such a big, important part of what we're going to need going into the future. Just a couple of weeks ago, there were a lot of news articles about the fact that we're just coming out of winter. We'd had a really wet one, and we didn't get a lot of water in our reservoirs. They were only half full. With the same amount of water in 1996, we had the local dam overflow. So it is a big issue for all of us that we're going to be looking at over the next little while. And it's a question of where are we going to get our water from in the future, and how are we going to manage that? Tonight we're very lucky to have 3 speakers that kind of cover the full range of that. So we're going to get this beautiful talk on how to maximize our groundwater. We'll get one more on desalination, and then finish off the evening on water reuse, which is a brilliant spread to be able to get. So without further ado, we'll get on with it. And I'd like to call Meegan Smith up to give our first talk.
Fantastic. Thank you everyone for the invite to this event. Yeah, it's an absolute pleasure to be here, and that's the best spread I have seen at any water function. And I was saying to a few people that I'm going to have to request it for the Hydrogeologist Association instead of just pizzas. So we'll see how we go on that one with the budget. Cool. Let's kick this off. So making the most of groundwater systems. Let's dive right in. Let's start with tonight's theme, reduce, reuse, recycle. I'm just going to take a slightly different slant on this slogan, given that I'm a hydrogeologist, and I'm going to be focused on the reuse component of that slogan. I grew up with this slogan in my childhood, and I believe, and I reckon subconsciously, it probably was a pivotal thing that enabled me to go into the science field in the environmental sciences, on top of having a good love of country and being in the bush. So this got me thinking, what's the history of this slogan? Don't worry, we're not going to be here for too long. I asked good old ChatGTP, because that's what we do these days, and apparently it emerged in the 70s as part of the rise in environmental movement for the first Earth Day. It also coincided with the creation of the EPA and the passing of the Resource Conservation and Recovery Act in 1976, which promoted recycling and waste conservation. So a little bit of history there, if you already knew that. Awesome. Let's get stuck in. So in terms of the reuse component of the slogan or the theme for tonight, I'm going to be talking about managed aquifer recharge, just real briefly, and just get the message out there. It's also known as ASR or aquifer storage and recovery. It comes under different names. So what is MAR? It's the intentional recharge of an aquifer under controlled conditions for later recovery, environmental benefit, or to mitigate impacts of abstraction. It can be very simple, including stormwater drains, storage dams, or they can be rather engineered, like injection and recovery systems. And you can obviously get very complex stormwater capture systems and the like also on top of that. MAR is successfully used worldwide and it's used for various reasons. It's a very adaptable technique. It's used for managing water supply, meeting legal obligations, restoring and protecting aquifers, maintaining minimum flows and levels, flood mitigation, water quality enhancement and protection, water reuse, ecosystem restoration and protection. So a whole slather of options of how this technique can be actually applied. General application of MAR in Australia is related to the capture of surface water, stormwater or treated wastewater, which is directly or indirectly recharging the underlying aquifer system to be later used predominantly for irrigation purposes or irrigation of green spaces. So what are we doing over here in Perth? Well, we have 4 well-known MAR schemes. Some of you in the room probably know a lot more about these schemes than I do, but this is just a quick snapshot on these schemes. So the first one and probably the biggest one is the Water Court Groundwater Replenishment Scheme. I think I was talking to someone just before about this. So essentially it's where wastewater from the Beanyap wastewater treatment plant is treated to drinking water standards and then injected into the local aquifer system. It's then recovered to supplement Perth's drinking water supply. And I honestly didn't even realise that that was a large part of our integrated water supply scheme here in Perth. The City of Mandurah uses wastewater from the nearby catted up wastewater treatment plant, which has been infiltrating via the use of infiltration basins into the surrounding superficial aquifer. It's essentially caused a mounding effect under that irrigation area, and that is then that wastewater is then abstracted and used for irrigation purposes on a green space by the City of Mandurah. The town of Cottesloe, the Mosman-Cottesloe Peninsula is underlain by a fresh groundwater lens overlying some salt water. The peninsula, unfortunately, is subjected to a bit of saltwater intrusion over the years due to a growing demand of groundwater resources being abstracted and also reduced rainfall. An opportunity developed where the town of Cottesloe could arrange manage aquifer recharge scheme to mitigate the intrusion of the salt water coming into that freshwater lens on the peninsula. The scheme's designed to hold and infiltrate a 1 in 5 year flood, capturing stormwater and using it to recharge, like I said, back into that freshwater lens. So that's sort of like using it for an environmental protection purpose, which is pretty cool. And finally, the Hartfield Park scheme. It harvests stormwater, which is destined for the urban water runoff system, runs through a filtration system and is recharged into the leadable aquifer via an injection system. They're using an injection system or injection bores instead of just infiltration galleries or trenches because of the Guildford clay, which acts as an impermeable layer. So it stops water from infiltrating down. In winter, they obviously harvest that stormwater runoff, and then in summer, they're able to abstract it out again and use it for irrigation purposes around those green spaces when that water demand is quite high. So Perth is those 4 quite well-known MAR schemes. If we look just across over to South Australia, they have over 40 MAR schemes and probably more, to be honest, operating across the greater Adelaide metropolitan area. predominantly used by local councils, golf clubs, to help improve their water sustainability and use and security, sorry. Essentially, South Australia is I like to call it, it's the hub of managed aquifer recharge. It's where a lot of the knowledge is in Australia. And then with discussions I've had with colleagues, it seems MAR is mostly promoted in that local government context over here in WA. However, private industry like mining, that's predominantly my background, we're definitely seeing a shift in momentum in adopting managed aquifer recharge as a water management solution. Whether that's managing surplus water from dewatering, protection of environmental values, and also in a mine closure context. When we talk about mining, we're talking about thousands of gigalitres of water that they've got to manage and handle. And that's thousands of gigalitres of water, of injection, infiltration, and essentially reuse and how they need to use it. Off the top of my head, the most well-known schemes in mining are predominantly up in the Pilbara, and they're managed and owned by the big players in the Pilbara. So that's the Rios, the BHP and Fortescue. So just a couple of examples of how MAR is also being used over here in WA and also in South Australia. So we were engaged by a client up in the Pilbara to undertake some groundwater modelling to help with understanding their drawdown impacts from mining and how that propagation extends into the Chemaraderies National Park. They had a trial MAR scheme set up close to that boundary of the national park, and they completed a trial, I should say, and we were engaged to model using that trial data and also their drawdown data to understand if the MAR scheme or the extent of the MAR scheme can actually mitigate the impacts from mine dewatering. This was a requirement from the regulator, so they sort of had to do it. So what do? We sort of looked at the very first stages. We developed the groundwater flow model to simulate that drawdown propagation from the mine dewatering and used the model to inform on an optimised MAR scheme to mitigate simulated drawdowns. Obviously, it was a multi-staged approach where we're essentially combining multiple models and multiple simulations and ensembles to get a nice sweep to understand that uncertainty range of if we were injected X volume across this area, what is that barrier that it's going to create and how does that work? And is it actually going to mitigate that drawdown? We also applied some particle tracking. That's this one up here, showing a bit of particle tracking just to help us understand where all that water they're injecting, where is it actually flowing under the hydraulic conditions. So what did this do? This enabled us to provide a preliminary risk assessment for the water quality impacts to the national park boundary. We also applied some climate variability to the model to help with those final water level triggers. Sorry. Another example how it can be used, ASR or MAR. It's essentially what happened over here. There was the reuse of wastewater treatment plant treated wastewater. Oh my gosh, to supply a horticultural enterprise with their irrigation. So essentially it was capturing water during winter when there was a surplus and then using it during summer when there's a higher demand. The treated wastewater was injected into the underlying aquifer system during the high periods and then obviously later recovered through the same injection, dual purpose injection abstraction bores. So we looked at the aquifer suitability assessment that looks at obviously all the aquifer parameters, so looking at aquifer thickness, hydraulic properties, water quality is very important. If we don't put any effort into the water quality side of things, it can actually catch us quite hard when it comes to implementation, especially in the operational phases also. It can become very costly. And we also looked at what's the impact of the proximity to other users in the area. In terms of technical aspects, we looked at clogging. Again, water chemistry changes from that injection water. Is it actually going to change the natural water chemistry within the aquifer, within the host aquifer? Matrix dissolution, local effects on the overlying aquifer, piezometric pressures, effects on the preferred aquifer, and the occurrence or the likely occurrence of opportunistic pathogens from developing and growing, I should say. We also looked at operational performance, so did a lot of modelling around the optimal injection rates, the extent of the injectant plume from the single well, recovery efficiencies, and the recovered water quality. There's definitely a lot of work required to get a MAR scheme up and running. There's a lot of legislation around it. All the states are very different, and it can make it very challenging to navigate and pursue, and for it to actually be an option on the options assessment table. Finally, the last example, this is probably one of the most common ones, similar to what we've already seen happening here in Perth. A golf course investing in the option of a MAR to support irrigation. Again, capturing excess water, sorry, excuse me, and using it for irrigation. This particular golf course didn't have the luxury of being able to use the groundwater of which they're on top of, because it actually became quite saline due to over-abstraction. So they had to think of another way of doing things, and again, MAR came up on the table. So in this aspect, again, followed a very similar process. Looked at the storage requirements of the aquifer, looked at their operational water balance, looked at the local hydrogeology, the implications that might have with injection water, and further investigate, and then we're obviously supported through the approval process to develop a MAR scheme. Right, just a nice short sweet one for you all. Summary and key takeaways. So MAR is very applicable for Perth and more broadly WA to help with water sustainability. There's opportunity open for all industries to adopt the concept of MAR, like I've sort of explained. It's in mining, local government, private use, wherever. And there's probably a lot of multidisciplinary action going on too, to be able to get a MAR scheme up and running. WA is in its infancy, which is an opportunity, I like to think of it, when it comes to MAR implementation and applying it as a value-adding option. So it's about trying to get MAR on that table in that discussion as an actual option. There's lots to learn from around the world. The rest of the world do MAR really well, especially over in Europe. And obviously our mates over in South Australia. They're leading the charge in Australia, I should say. There's, like I mentioned, there's a big link with MAR and water chemistry, since a lot of you guys probably have quite a big chemistry background. I thought I'd better call that one out. Clogging is a major issue with MAR. If that's not addressed early on in the piece, again, it's going to cause lots of operational issues, and then that puts the whole MAR concept with a black stain against its name because it's not working, we can't inject the water, it's clogging up, all those type of conversations. But if you're on top of it nice and early, there are ways to be able to mitigate that. And obviously, the other link there is the detrimental effects to the aquifer system. So making sure there are no detrimental impacts to the native aquifer system, which Water Corp have done a great job of essentially putting way cleaner water back into the native Nangara mound than what is actually there. And that's it. That's me. Thank you very much.
Our next speaker is Brad Albright from Jacobs and going to take us through some desalination.
Thanks everyone for turning up. I've taken a little bit of a different tact. Apologies for the slideshow, but rather than make this too technical, I'm going to run you through a couple of case studies and show you where we're at the moment on the Alkimos seawater desalination plant, which is full steam ahead at the moment. We're probably about, I don't know, maybe 15 or 20% of the way through the construction phase. So just a little bit about me. I'm an ex-graduate here at Curtin University, finished my PhD here, feels like a long time ago. Now, before moving across to industry, first worked on the Kwinana desalination plant, so that's 2005-06 timeframe, and been in the industry ever since. So just tonight we'll run through a little bit about osmosis and reverse osmosis, give you a run through on desalination, and then sort of show you what's happening at Alkimos out of interest in terms of large scale desalination. So that's me and our mechanical lead engineer down in the intake shaft at Alkimos only a couple of weeks ago. So just to give you some context, and the picture on the right there is just before the machines that are going to drill the tunnels out under the ocean. One of them's, I don't know if this is going to work here, let's see how we go. This one here's gone, and this one here is about to launch, and that's me just standing over here to give you an idea. The launch shaft here, that's about 50 odd metres in diameter, and we're about 45 metres in diameter here, so just for some scale. So this is going to not be anything shattering for anyone in the audience here, but the central premise of what we're talking about here is osmosis and how we're going to overcome that. Again, a fairly well understood concept on what osmosis is and sort of nature's way of achieving equilibrium. The important thing, I guess, here is just sort of having a look at type of the pressures that we're trying to overcome. Obviously, you can calculate osmotic pressure. Osmotic pressure of seawater, we're sort of talking in the order of 25, 27 bar at 35,000 milligrams a litre, which is the salinity of seawater. So these are the type of things that we have to overcome with reverse osmosis, and as I say, just an easy way to demonstrate that. As we say, we're trying to achieve equilibrium, and this is what we're talking about into the height difference. So this is the central concept of reverse osmosis, is overcoming that. So I've got a picture here of the second desalination plant that Water Corporation constructed, Binninyup, just north of Bunbury. This is one half of the plant. So this is the first pass RO system here. So inside there we have just over 30,000 RO membranes sitting inside a little over 400 pressure vessels in 8 sort of racks. So this setup here is delivering sort of around about 10% of Perth's water just in this room here, producing sort of 75-80 megalitres a day of drinking water. So just to give people some idea of scale of what we're talking about. So just a picture. This is Ulrich Boss, who was the commissioning manager of that project. But this is the first pass high pressure pump. So we're taking about 300 litres a second of water there and increasing the pressure of, at this point here, from about 2 bar to a little over 60 bar on a continuing basis. So yeah, just so everyone's got an idea of the scale of what we're going through here. So this is just a simplified flow diagram of a reverse osmosis system for producing drinking water. So what we've got is filtered seawater. I'll talk you through a bit of the pre-treatment, which is sort of the crux of what we're going around here. Boosting the pressure through a first pass RO membrane. One of the things that that makes this kind of quite economical is we only treat a portion of this water through a second pass system. So all of the seawater going through here, the purer water that's generated by the first few membranes in a pressure vessel bypasses that second pass system. The less pure water we're treating again to get the product salinity down as low as possible, and then that water's being sort of disposed. I'm just going to run through here. Something I'm going to talk about in a second, and the thing that really makes seawater desalination possible is energy recovery. I mentioned before about the amount of pressure that we have to generate. It's a very energy intensive process. Without this energy recovery portion of the plant, it's questionable whether desalination would be a viable method for producing water. So if you think a turbocharger on your car, that's effectively what we're doing here, and I'll run through that in a little period of time. But we're taking the energy that exists in this brine stream, again, which is sort of 60 bars worth of pressure, and converting that so that we pump a smaller portion of that water. So that's the reverse osmosis process. Again, in 15 minutes, it's sort of a bit difficult to get into too much detail. So what I thought I would do is run through a case study, and this is Alkimos. So I don't know if you're familiar with the area, just sort of south of Yanchep here. This is the Alkimos plant last week. So this photo, we fly a drone up there on a weekly basis, and this is where we're at from a construction point of view. So the Alkimos wastewater treatment plant, Alkimos as a suburb, sort of just down here, sort of Marmion Ave's just about here somewhere. So as I said, about sort of 20% of the way through construction, and yeah, that's what it looks like. So this is the desalination process at Alkimos. This is just a sort of a simplified block flow diagram so everyone can appreciate. You don't sort of have to take too much into account what's going on here. I'll sort of talk you through it a little bit, but as a process, what we're talking about is taking water from the ocean, and I'm going to show in a bit of detail these in the sort of coming slides. So bring in seawater from a couple of kilometres off the coast, intake pump station, which is what I was standing down inside of on a couple of slides ago, pumping that water. This happens under gravity. It's just sort of a glorified, sort of a simple U system. Take water off the coast and bring it into a pump station, then gets pumped through our process. From a desalination process, even though the RO is the heart of the plant, the pre-treatment system in itself is probably the most important thing. Pre-treatment fails, and your reverse osmosis process is very compromised. So this is removing the solid component. RO membranes are quite susceptible to solids, so we're taking out near 100% of any suspended solids inside the water inside this process here. Reverse osmosis, taking that very pure water and removing the salt, which we'll get into. We produce water in an RO system that's too pure. The salinity, or the the dissolved solids post RO is in the order of 50 to 100 milligrams a litre, something in that order of magnitude. We're then increasing the alkalinity, the pH, so it's suitable for drinking, disinfecting, and adding fluoride so your teeth don't fall out. Finally, pumping water. The water from Alkimos is heading to the Wanneroo Reservoir, so it's sort of 25 odd kilometres away. It's also, we're at about an RL of 10, so sort of 10 metres above sort of mean sea level, and Wanneroo Reservoir, don't quote me on this, but I think we're talking sort of about 80, 90, 100 metres above where we are now. So we've got to lift that water 300 megalitres a day, 100 odd metres in the air. So just stepping through from a process point of view, apologies for the image here, I could have maybe done a bit better here, but it was sort of a bit last minute. This is a hydraulic profile of our intake system. So as I was saying, in terms of level, we're at minus 25 here, and then sort of if you look on shore, I think I've got haven't quite, the ground level on shore where we are up here somewhere is at about RL10. So this water eventually the tunnelling machine, which you're going to see in a sec, starts off just in here, makes its way down to minus 25. The tunnel in itself is 2.5 kilometres long and 3.5 metres in diameter. So that's how our 600 odd megalitres a day of water is making its way onto shore. Seabed here, so RL25 to 10.3, so we're about 15 metres below the seabed where the tunnel finishes. This is the connection with the ocean, and you can see up here we've got a couple of tide levels: lowest astronomical tide, highest astronomical tide, and then a theoretical highest astronomical tide with a sea level rise out to 100 years. So effectively what happens to get water on shore is just flow all the way through this tunnel, and then just it sits here under gravity. So this is what the intake pump station looks. I've taken some snips here from our design model, which is where all the construction deliverables are generated from. So this is this is the tunnel here. This is the inlet, so this is where this machine, which is just sitting here, it actually launched on Monday, might have been Monday or Tuesday this week, started its journey. It goes through that little hole there, and this red line's just sort of showing where we're going. So through some isolations here, we've got a stop log and a penstock. This device here is a band screen. We're sort of filtering water to about 6 millimetres in size, so taking out sort of bulk solids, and then here's our pumps in here. So as I say, for some context, this is about 50 metres in diameter here, and about 20 metres deep. So that structure was constructed earlier this year, and these particular works have been in the makings for sort of the last 6 to 9 months, preparing for the tunnels to launch. They take about a year, the journey of the tunnel boring machines. The long one, which went first, that takes about a year, and we're sort of about 7 or 8 months for the intake tunnel before it's drilled. So the intake pump station. Just for some context, I took this photo, I think in maybe about, I'm trying to say May, maybe about that sort of time frame. So this is the tunnelling machines before they launched. As I say, 3.5 metres in diameter, internal diameter of the tunnel. It's them ready to go. So pre-treatment, as I said previously, this is almost sort of the most important part of the process. If your pre-treatment fails, the RO membranes end up with a lot of restoration work that needs to be undergone, chemical cleaning, replacement, etc. So the Alchemos process, we have a dissolved air flotation system and a gravity media filter in a single structure. So what I've tried to demonstrate here is the flow path through that system. This is about 80 metres length and sort of 40 metres in width, just for some context. So water's entering the front here through this flow path here. We have coagulation and flocculation to remove that solid material. Then makes its way up and over through some mixers through this tortuous flow path to give ourselves a retention time inside of these two chambers, and then flows up over a weir and through this central channel. We have 2 streams. We've got 9 cells on one side, 9 cells on the other, 18 in total. They sort of run in a n-2 arrangement, so we can have two off at any one time on each train, one out of service, one to backwash the system. This is just sort of demonstrating the flow path through this train. So the dissolved air flotation portion at the top here to float off any of the sort of the bigger material, and then anything left behind. It's not shown on the model here, but we have filtration media out through that process. Again, this is this week where we're at from a construction point of view in the process. So the RO is sort of the heart of the plant. Again, simple demonstration of the flow path that we've got going through here. So there's a cartridge filtration, so this is taking sort of everything larger than 5 microns out of the process, and then 2 equal trains. Here's our first pass. We have in this plant 3 in train stage A and 3 in train B. First pass permeate gets sort of conveyed along the central corridor, and then a portion of that second pass on side of each side of the plant here. So what I really wanted to sort of demonstrate, and I was talking before about the heart of the sort of the thing that makes this all possible, is our energy recovery system. So this is taking, if you imagine this is our membrane system here, we're taking the high pressure reject stream. So this is our brine flow. If water is entering the membranes at 60 bar, it's leaving the membranes here at sort of 57, 58 bar. And what we're doing in this process is recovering that sort of energy inside of the system. So it's a very simple process that's highly effective. We're sort of recovering maybe 95+% of the energy that's embedded inside this stream, and all that happens is the rotor inside of here is spinning around. Fresh water's getting fed in. As the rotor spins, that pushes a stream of fresh water out the other end, and then the brine that has then lost that, I guess, energy is just pushed out by a waste, and all we're doing with this sort of circulation pump is just making up any energy losses through the system. What this allows us to do is effectively pump half or a little bit less than half of the flow through this high energy pump, which you saw before, and the rest of it just has a little bit of a boost to get the pressure up. So it's effectively taking away half of the required energy to produce this seawater. If not for this process, as I said before, it's sort of questionable whether reverse osmosis as a desalination process becomes economically viable in a lot of applications. So that's that for our purposes. This is how it looks like. Again, here's the energy recovery system. We're taking the brine, it's getting passed through these energy recovery devices. These are just manifolded together, and then the low pressure brine is out to waste. What happens in this stream is we've got low pressure filtered seawater. Again, the energy is boosted. It goes through this much smaller pump, combines with the high pressure from the high pressure pump here. About 40% of the flow in this stream, 60% of the flow in these stream. These two things get combined, make their way through the RO membranes, and that's how it all works. Just finally, I've just got a couple more slides. Hopefully I'm going okay time-wise. Just for some context, there is 50 megalitres of storage for this water. So we're sort of talking in stage 1, sort of 8 odd hours of storage. In stage 2, maybe about 4 hours of storage. Hope I got the maths right there. And delivered through the pumping station up to Wanneroo Reservoir. So sort of nothing too complex about that. One thing that I did want to touch on, maybe a bit of chemistry to finish off, just for everyone's benefit. Something that's quite ingenious, I think, in this process. Certainly the first time I'm aware of it in Australia, and I don't actually know of another application elsewhere in the world where this is being done. But we're taking treated groundwater from the Eglinton groundwater scheme, so relatively deep aquifer in the north of Perth, and that is getting blended with the permeate prior to disposal. So this is quite high alkalinity groundwater, and what this has done in this instance is reduce the chemical demand by sort of up to 50% of this process. So I was talking before about the remineralisation that we need to do to bring permeate sort of up to drinking water standard. By blending this relatively high alkalinity source, we're cutting the chemical demand at Alkimos by about 50%. So that's sort of hundreds of thousands of dollars years of savings, producing exactly the same product that we would do without that process. So that's it. This is what it's going to look like at some point in the future. Just a bit of a sales pitch, but yeah, it's tucked away in there. You know, sort of see what's going on. And as I say, looking forward to talking to anyone about it at any stage later on. Thank you very much.
Our last talk of the evening is from Neil Bartholomew from Proxa. So thank you very much for all the yummy food.
Thanks everyone. I'll be talking a little bit about Proxa, so I'll apologise if there's a little bit of a salesiness to the beginning, but I guess the reason being is most people may not have heard of us. We're a relatively small organisation within Australia. So I'm going to go do a bit of a Proxa overview. I'm going to talk about two case studies related to water. So one is fluoride treatment, and the other is the use of reverse osmosis in the battery metals and rare earths processing, where we've had quite a bit of work in recent years. So who are we? Where do we support? And how do we support? So picture of us there in front of a seawater desal plant. A group of our team. So now I'm not going to read this, a lot of words. This is one of our generic guff slides, but I guess the key one for me is the way our organisation is structured and the way our business runs is we basically are focused on solutions related to the needs, right? So we don't have a package or a widget or a particular pump or a unit that does a thing. We're really looking at what we see across the industry and what we can do in terms of the gaps within the water treatment space for plants. So we work across all areas in water in the cycle with typically more industrial sites and less the desalination sites. Working in the raw water, recycling within plants, which is I was enjoying the reduce, reuse, recycle section, which is a big focus with water scarcity that we see across Australia. In terms of industries, we're working largely across all industries, but predominantly we see a lot of work with the mining and mineral sector and a little bit in food and beverage and municipal. This is interesting to me. I suppose I've spent, and I should have said my background, Tamsin, I'm sort of probably just a bit nervous standing in front of so many intellectual people today. It's a bit of an unusual crowd for me. But I suppose one of the things that makes my job quite interesting is I've been involved in water treatment for about 25 years in different roles and different businesses. And, what we do is very much across the whole cycle of the project. So surprisingly, a lot of my time was spent in an operational space, but the most impact you can have to a project and the water balance and the water, use is in the design phase. So a lot of the work that Proxa does is working with clients that are in very early stages of development, so in PFS and DFS, where they're working through what they're doing with their water balance and their solutions, and working with some of the engineering houses like Jacobs and a few others. So, but lastly is this area closure, and we were talking with, another engineering house yesterday. We were talking about the number of closure projects around the world, and I suppose this comes down to, as regulation has increased around the world, we're seeing a lot more focus across all industries about the requirements of water management and, I suppose, to simplify, make good after you've left a site. So it's an area that we spend a bit of our time in as well. So I'm going to be talking a little bit about these early stages. So we talk about looking through the whole project life cycle. And in terms of our organisation, that we find that usually makes us somewhat unique is we spend a lot of time in the R&D space and the design space. So people often ask, what do you have? What are the units you got? Do you do RO? And that's usually a pretty common question because that's what we hear about when we think of desalination. I suppose, I've listed, I'm not going to read them all, I've listed some of the unit processes and applications that we do utilise. And I suppose this is the key. Our organisation is very heavily leveraged towards, I'm just going to use the word intellectuals again, intellectuals and technology and R&D. So we spend a huge amount enticing people of a strong technical nature into our business. What's unique about what we do is we don't tend to do as much standard plant So yes, we do a potable water treatment plant. As someone will ask me, oh, do you do potable plants? Okay, yeah, we do. But that doesn't excite us. And what's really interesting about our organisation is when I bring one of those curly problems to the team and go, hey, we've got this, we may not want to touch this. And they go, no, that sounds interesting. And everyone gets in and steps in and gets involved. So we'll leverage a lot of these different technologies regardless and try and do something with some very difficult water. So this isn't too difficult, but this was an interesting one that we came, so I'll go through case study 1. It was around about fluoride removal in industrial water for discharge. So if we talk about environmental considerations, a lot of our clients take their water and they may then have to discharge it to the environment, whether that can be rivers or the aquifers or wherever, and we've got to make sure it's up to spec. So in this, and I went for the theme, sorry, as Tamsin gave me, of innovation and research. So I used the AI tool that I'd never like to use for definitions, but I thought I'd just put this in. I spend a lot of time, yes, working in a sales role, and we throw out that word innovation all the time. And for the last probably 15 years, someone said, yeah, it's innovative. And I suppose I like this one because it's about implementing new ideas that generate value, right? So what I'll also say is sometimes a new idea for one client and one industry is an old idea for someone else, right? But it's still considered innovation because we've made a step change for that client. So, and research, as I said, is a cornerstone of how we do what we do. So this is a good flow sheet where we had a problem. They had fluoride issues in their waste stream. Industrial site, I won't really say more than that in terms of non-disclosure. And we had a waste stream fluoride of anywhere between 60, I say 160, but sometimes 200, sometimes 300 ppm of fluoride. So this was considered far too high, and they kept getting those letters from the regulator that says, yes, we need to be less than 30. So they wanted to look at treatment processes where we could manage that. And so, and this is really where that innovation and research aspect comes in, is we took an approach where we went through multiple stages to help our client get a solution, which included a desktop study, lab test work, all the way through to a small pilot trial to validate the process, and then looking at full-scale execution. So we were looking at different methodologies about what we can do. Yes, we still read the literature, so we appreciate universities making more research, more literature. That is important. We have our global R&D group that the Brains Trust, if you will. And so in that first stage, we look at the desktop process design. There's a lot of focus on CapEx and OpEx, right? So, you know, we have to deal with the commercial realities of life. We can't just say, yes, I can make this work. We have to go, is that going to be effective in terms of a cost expectation? So typically in this space, it's a high level, can we do it? What are their options and what is it going to cost? So we looked at 2 methodologies. We're looking at calcium fluoride precipitation and also the fluoroapatite process. So we progressed from that to the lab test work, and I don't have all the pictures, but I put up a few. And for those in the room that have done coagulation, flocculation test work, it looks a lot like this. It can take hours and hours and hours, and it doesn't always get results. But good news is both of these were effective. We got good settling rates across both. Some slightly superior. I think the fluoroapatite method was a little bit superior in terms of the settling rate. And the big issue was what was the residual fluoride that we were seeing. And that was really helping us determine, as you do this test work, what is the size of a clarifier that you need, which then goes to the CapEx and OpEx portions of the design. So we were able to refine the estimate and then say to the client, yep, here's what you could build, here's a process solution that'll take you out of a risky environmental condition into where you're getting a big green tick from the regulator. However, as many clients do when they're going to spend, plus millions of dollars, they wanted to have a look at a trial validation. So again, coming at it from, dare I say, a research and testing point of view, we've got a lot of pilot equipment within our fleet. So we do lots of those unit operations I showed on the earlier slides, that we have lots of lovely pilot test work. So not too dissimilar from things that we do see in the research space. So we took to site this is a lamella clarifier, very small version with the lamella plates inside, and we did a 2-month trial on site. And what happens on the beaker or the column is very different to what happens on site. So this is where graduates come in. It's a fantastic job for graduates. Our graduates spent 2 months on site, some challenging issues with feed qualities, different fluoride levels, which I'll show you on a graph in a minute, and pH stabilisation. So, you know, by means when we have a pilot unit, I'm not saying it's not bad gear, but it's very different engineering to what you'd have on a full scale, right? Oh, do you have 2 sets of pH control? Have you got data logging? No, we don't have all that, but we've got most of it. And so doing piloting always comes with the challenges. But we had, in the end, some very good results. We got a 75% removal. We were able to achieve a less than 30 ppm, which was the target. In fact, some of the time we got down to 20. This graph here shows that we did the test work in winter. So if you're doing wastewater test work in winter when it rains, turns out you don't really have a problem in winter, so we kept trying to solve a problem that wasn't there. So our graduate had to get a truck each day, find some waste of the concentrated version, get the truck guy to drive it around the site to mix it in the back of the tanker. It was a lot of fun. And then we did some testing. So we actually did 3 different scenarios. This one in Block A and Block C were more indicative of the typical variability of the waste, in which case we always got the overflow down below the 30 ppm mark, which was great. And we had a period where, I want to say it was a lab analysis issue, I think, Andre, in that instance, where the lab was reporting something and the ratios of mixing in the back of this truck were wrong. So we thought, geez, we're really struggling to get below the mark, and we were, but we actually were able to prove the process for much higher ranges of the fluoride coming in. So the client was able to actually go home with the satisfaction that we've tested and trialled a solution that even if they had those upset conditions in their industrial site, they wouldn't have an issue. So that was a real win for us, and I suppose at the end that gave the final, you know, the goal of any organisation like ours is, and not just us, but obviously the client, is to get confidence in the final solution and moving forward to full-scale execution. So Proxa is a global organisation, and I left out the slide with the globe, but as you can see, this is probably not made in Australia, but we are making, at present, a number of lamella clarifiers actually here in Perth, so for a different project. But yeah, so we go through that and we manage everything from the project management, the fabrication. We can either install or do supervision, and then go through commissioning and performance testing. So this one's not here and not fully installed as yet, but it's on its way. Yeah, so that's our first case study. Second one is really focusing on membranes, and I know that was one of the other topics which we've heard quite a bit about, which was fantastic, so I don't have to go and talk about reverse osmosis too much, which is, I appreciate that, that was good. More technical than I was ready to go. But really it's about what we see in industry in Australia and Western Australia, and one of those hot topics in the world at the moment is all about battery metals and rare earths. So if anyone saw the news this week, this is a hot topic of conversation. And as we talk about, you know, water scarcity and aquifer recharge, it's that availability of water. So one of the things that we see is that battery metals and rare earths really require a good quality of processed water. So depending on where you are, I'm sure everyone's familiar, there's some plants in Western Australia that are fairly remote, and typically the water that you get out in these areas, so I lived in Kalgoorlie for a while, the water in Kalgoorlie can be 100,000 to 200,000 microsiemens. And I personally looked after plants in a different life where we used 200,000 microsiemens, and that was their processed water. It's not really friendly. Not as bad as this for some of these guys, but essentially it's a big focus for these types of clients to have a better quality water. So, reverse osmosis. Oh, I've jumped ahead of myself. I'm talking and I had a slide for it. Yes, we do see typically some of the bore water is the better stuff, is that 3,000, 5,000, maybe up to 10,000 mark. But you can go higher, as we've talked about seawater membranes and higher pressure. The typical impurities that are a problem are calcium, magnesium and sometimes boron, but there can be a host of other things depending on the process. Certain species will poison different aspects of the process, but what we're seeing in lithium and rare earths, and certainly in the flotation space, is, the impurities can have a very big impact on the yield. So even, 10 to 100 ppm difference can have an impact of like 5 to 10 or 20% of yield. So when you're talking about an industrial mining refinery, that's something that upsets management. They tend to get a little bit upset. In some instances, and we've done some modelling for PFS in certain projects at the moment, we're talking calcium magnesium down to 10 ppm. So for those that worked in a lab and said, oh, calcium at 10 ppm, that's pretty much background. Like, it's really hard to get to that level of purity. So needing that on an industrial size scale for a mining operation can be quite a challenge. So when we're talking about membrane processes, and I really want to state, I love hearing the fact that it's all about treatment. So if we look at sort of some of the types of processes we can get to, 3/4 of that PFD on the right as a typical example is on pre-treatment. It's really all about getting the solids out. The reverse osmosis process is really just getting the final salts and getting us to the purity we want. So you've got different levels of reverse osmosis, brackish water that we just talked about, high pressure, and then ultra high pressure. So for those that haven't heard of ultra high pressure, we're now talking about up to, I think we just heard, was it 60 bar? Ultra high pressure in some cases will get us to 115, 120 bar. So it's got its uses in terms of concentration, but then also polishing RO. Put the last one down because it's a bit of a fun fact, is that a lot of people that are, I'm going to say, non-technical backgrounds, they expect the water to go in the black box and come out the other end nice and clean, and they don't really account for the fact that it has a waste stream, right? So we get clients going, oh, but you've got all this waste. It's upsetting our water balance. And we said, yes, that was in the design sheet. So it's something that I suppose a lot of clients, when we go and talk to them, and I'm sure some of you are in this space and have had these conversations, brine disposal management is something else that we see that comes up as a challenge for these clients. So I've got a few examples of projects that we've been doing in Australia, and we've got one here. Again, it's bore water feed. We had initially a fairly simplistic design of multimedia filters and then RO, but the design was upgraded later for an additional 2 ROs. And what that was really doing is running a second stage to treat the brine and improve the recovery. So this is the layout here. And I suppose it's probably a good time to mention that what we're seeing a lot in industry with water at the moment is it's all about mobile units. So the cost of labour in Australia is somewhat high. Building things in remote locations can be very expensive. So modularisation and the ability to get something to site and do the absolute bare minimum of install. So that's why you see things like 40-foot containers with HDPE piping across the top. This is another similar facility. This one is in commissioning at present. So we've got, again, very similar multimedia filters. You've got the vessels outside, and you've got all of the control housings inside the container. And then we've got the RO systems with varying stages of pressure as it goes up to look at that increased water recovery so that we're not wasting as much of the scarcity of the bore water that they do have. Final one that I wanted to share in terms of reverse osmosis, and this one I don't have any finished pictures because it's still in fabrication and manufacture, is another rare earths client in Australia where we've got 2 reverse osmosis plants which are all in the nice 3D layout there. I suppose what's really interesting with this is that this one, rather than being at the front end or the back end where it's raw water treatment or final wastewater treatment, actually sits within their main process stream. So again, water scarcity, how much you've got for pores in your aquifer. These guys probably reprocess, I think it's something, a large percentage, I won't name the percentage, in terms of the design, so that they can manage their water balance. So it's really critical that we can take it, and there's quite a few pre-treatment stages outside of this box to make sure that they remove contaminants or any other solids before it goes through our package. So it's very interesting, it's very exciting, it's good to be getting involved with these type of projects. That's all I've got. I hope I was quick enough. Great.
We have little presents. So thank you very, very much for night.